Look around your city, and you are looking at the second most consumed substance on Earth, cement. It is so ubiquitous that it has become effectively invisible to our daily lives. People often use the terms cement and concrete interchangeably, but there is a distinct difference. Concrete is the final product, the gray rock forming our sidewalks and bridges. Cement is the active, binding glue that holds all the sand and gravel together. Creating this glue requires sustained temperatures of 1,450 degrees Celsius. Maintaining that industrial fire around the clock is why. This single material accounts for roughly 8% of total global CO2 emissions. To understand why we rely on such an energy-intensive process, we have to deconstruct how we turn ancient rocks into the modern world. We are now in a race to find a new recipe, one that preserves our ability to build without the environmental cost. Builders have used variations of this binder for millennia. The Romans mixed volcanic ash with lime to create structures that still stand today, but the modern industry began in 1824, when Joseph Aspdin patented what we know as Portland cement. The core ingredient in Aspdin's recipe is limestone. We mine it in massive quantities because it contains the one thing the chemical reaction requires: calcium. That calcium has a biological origin. Limestone is formed from the fossilized shells and skeletons of prehistoric sea creatures that settled on the ocean floor millions of years ago. The entire cement industry is essentially a machine designed to extract that ancient oceanic calcium and force it into a new synthetic rock called clinker. The process begins with raw extraction. Mining operations use controlled explosives to blast limestone and clay from the earth, producing thousands of tons of jagged rubble. This rubble is crushed, homogenized, and meticulously blended to ensure a consistent chemical profile. Huge mills then grind the rock into an ultra-fine powder known as raw meal. This raw meal is fed into a precalciner. Inside these towering structures, the powder is suspended in a rising column of high-temperature gas. At approximately 900 degrees Celsius, a reaction called calcination occurs. The heat causes the calcium carbonate molecules to fracture. They split into two parts: lime, or CaO, which we need, and carbon dioxide. This chemical split is the moment the environmental damage is triggered. As the useful lime moves forward, the detached carbon dioxide gas escapes directly into the atmosphere. The precalciner is highly efficient at preparing the raw material, but this necessary chemical separation creates the very emissions crisis the industry is now trying to solve. The lime now enters the rotary kiln. This is a massive, rotating cylindrical furnace where the material is heated to 1,450 degrees Celsius. Inside, a process called sintering begins. The materials do not melt into a liquid. Instead, their chemical bonds break and fuse together to form new calcium silicates, known as alite and baelite. The immediate output of this furnace is clinker. It emerges as hot, rounded nodules that serve as the essential intermediary for all modern cement. Those nodules drop onto a series of parallel metal grates in the cooler. High-pressure fans blow cold air through the grates to rapidly drop the temperature of the material. This cooler is a critical part of the plant's efficiency. The air that chills the clinker absorbs its heat and is recycled back into the kiln as tertiary air, significantly reducing the amount of fuel needed for combustion. Finally, the cooled clinker is mixed with a small amount of gypsum to control its future setting time. Steel balls in a finishing roll pulverize the mixture into the fine powder we recognize as cement. The cement factory is a giant closed-loop thermodynamic engine engineered to force ancient calcium into a highly reactive modern state. We have spent 2 centuries perfecting this material, but the chemical cost of the current recipe is no longer sustainable. This chart shows the emissions challenge. Roughly 35% of a plant's footprint comes from burning fossil fuels, but 60% is caused by the unavoidable chemical release that happens during calcination. To address this, the industry is pivoting toward a new standard, Portland limestone cement, or PLC. PLC replaces up to 15% of the energy-intensive clinker with raw, unburnt limestone powder. By skipping the kiln for that portion of the recipe, the carbon footprint drops by 10% without sacrificing structural strength. Beyond that, a new mixture called LC3 uses calcined clay to drop the clinker requirement even further, down to just 50%. The immediate challenge is to rewrite our foundation's chemical recipe, perfecting a cement that provides the strength modern cities require without the environmental cost.